So good evening, everyone, and welcome to tonight's presentation. Tonight's presentation is going to be, as Mike said a few minutes ago, about the life cycle of stars. And my name is Chanan Greenberg, and I used to be a board member and vice president of the San Mateo County Astronomical Society, and today I'm a long-standing member with the society for the past 17 years. So with that, let's get started. Today, we're going to talk about the life cycle of stars. And as you can see in this diagram, which kind of captures a summary of what we'll be discussing tonight, star formation starts with stars forming inside a cloud of gas and dust, or a nebula. And based on the mass of the star, they can either evolve as a small star, a low mass star like our sun, becoming a red giant, a planetary nebula, and ending their life as a white dwarf, or they can become massive stars, supergiants, and end their lives in a very violent supernova, leaving behind various remnants like neutron stars and black holes. Now, we will basically today go through explaining all of these cycles and a bit about the physics that goes on inside the star that drives the path that it will evolve as it matures. And we will start from formation and all the way through to end of life and what is left behind. Since we'll be referring to some recurring themes in today's presentation, and we'll be referring a lot to the balances between certain forces, we'll start the presentation explaining a few basic concepts about how stars work. We touched on this in the prior presentation we did last month, but for those who were not here last time or don't remember it from last time, we'll explain it again here so that these themes that we will refer to multiple times during the presentation will be properly understood. We'll talk about how stars evolve. We talk about life cycle in general. Obviously, stars are not alive, not in any sense that you and I would relate to, but it's easy for us to talk about the stages of stellar evolution in the form of a life cycle. So we'll start about the birth or the formation of stars, go through life on the main sequence, a concept that we will explain where stars spend most of their life, and then we'll discuss what happens when they run out of fuel. And you'll see that we diverge when we're dealing with low mass stars and high mass stars. And we'll talk about what happens after they die. What are the remnants that they leave behind in the form of white dwarfs, neutron stars, and black holes? Now, throughout the presentation, number one, I'll just remind again, if you're not asking a question, try and put yourself on mute because it'll minimize any feedback or background noises. However, I would love to keep it interactive. So if there are any questions throughout the presentation, just feel free to come off mute and just ask a question, or you could type your question into the chat and Lisa, who is tracking the chat, will be able to notify me about any questions coming in. So we'll try and address as many of those as we go through this. So without further ado, let's talk about a few very important concepts, which we will be coming back to many times throughout today's presentation. So we'll take a few minutes to make sure we all understand them. The first thing that we need to understand is a thing called the Kelvin-Helmholtz mechanism. The name doesn't really matter. What is important is what it does. Stars are balls of gas, and as balls of gas, they are ruled by the rules or the laws of hydrodynamics, which means that the laws of gases apply to the way a star behaves. And specifically, this ball of gas, the star that we're talking about, is held together by a balance of two forces. There is the force of gravity that is trying to push everything down and crush everything to the smallest, tiniest point that it can. And fighting gravity is pressure pushing up, the pressure of gas pushing up. In order to have a stable star, a star that is not contracting or expanding or just doing crazy things, you need to have a balance between these two forces. This balance, called hydrostatic equilibrium, the balance between gravity and pressure, is a prerequisite to having a stable star. Now, for those who attended last month's presentation, you may recall that this mechanism was one of the ideas that was postulated as one of the methods in which a star can generate energy, where the star contracts, the heat goes up, the pressure goes up, it's releasing some of that heat, it achieves a balance, more of that heat dissipates, the balance is lost, gravity pulls in again, the star contracts again, gets hot again, and achieves balance. As we discovered in last month's presentation, while that mechanism can generate energy that would fuel a star like our sun for about 30 million years, it's nowhere nearly enough to keep it going for billions of years as our sun does. And so what we find is that in the core of a star, about 10% of the total mass of a star, there is nuclear fusion going on in that heart. And that process is generating tremendous amounts of energy that allow the star to generate as much energy as it needs to keep it as luminous for as long as it needs, or as long as it can, as long as it has fuel in the heart of the star. So basically, that this process of nuclear fusion is taking light elements. In this particular case, we're talking about hydrogen. We take 4 atoms of hydrogen, we fuse them together. We won't describe the fusion process here. We covered that last time. We're fusing protons together, and these protons produce a heavier element called helium. And from 4 protons, or 4 atoms of hydrogen, we get 1 atom of helium. And the 4 protons weigh a little more, about 0.7% more than this 1 atom of helium. That process of fusion converted some of that mass into energy. And that energy is released in the form of positrons, which is antimatter, and in the form of neutrinos, which are tiny, very, very powerful particles, almost massless, moving almost at the speed of light, as well as photons, which is the light that we see. So as a star is shining, its luminosity and the heat that it's losing into space, it needs to compensate for that loss of energy by generating energy in the core. And that is what is happening in nuclear fusion. And in order to be a stable star, it needs to produce in the core as much energy as it is losing. Otherwise, again, it will not be a stable star for a long period of time. So the bottom line is, to be a stable star, you need to be in both hydrostatic equilibrium, the balance between pressure pulling out and gravity pulling in, and thermal equilibrium, that the amount of energy you're producing is equal to the amount of energy that you're losing as a star by shining away through your luminosity. And the last concept that is important to understand is that the bigger a star is, it has more surface area. If it has more surface area, it's a bigger ball, it will shine away more light. So if it's shining away more light, which is the equivalent of saying it's losing more energy, it needs to generate more energy in the core. So the bigger the star is, the more luminosity it has, the more need it has to generate more energy in the core of the star. So these are 2 very important principles that we'll be referring to throughout the whole cycle of stellar evolution. Starting with, again, I'm just going to repeat them here quickly. We have to have a stable star. We need to have a star that is in balance between gravity and pressure, and in thermal balance, how much energy am I shining away and how much energy I'm generating in the core. So before I continue, because this is really important, I just want to check with the audience and see, is this clear, or are there any questions people have? So far, so good.
Helium has an atomic number of 2, not 4. It's 2 protons and 2 neutrons.
But the
Correct.
atomic weight is 4.
Correct. But when you take the mass, when you measure the mass of 4 protons versus 1 atom of helium, which is made of 2 protons and 2 neutrons, you will find that there is a 0.7% difference in the mass.
So there's beta decay going on inside.
Well, it's actually in the process, again, we're going down into proton-proton chain reaction, which I wasn't planning to do here, but in the process of converting protons into neutrons, when you have the proton-proton chain reaction, one of the protons converts to a neutron, and in that process, it loses a positron, which has some mass. It also uses a neutron, which also has some mass. And in that process, so that is the process in which you're converting some of the mass that was there into energy. It's a tiny amount, but it's enough to be a difference, and that tiny amount generates a huge amount of energy. Any other questions?
So,
Okay. So let's start with the first phase, the birth of stars, or as we refer to it here, star formation. Stars form from giant molecular clouds of gas, primarily hydrogen gas. There's obviously other elements and dust in there, but it's primarily hydrogen gas. This picture that you can see here on the right-hand side is showing you an actual molecular cloud. This is part of what is known as the pillars of creation in the Eagle Nebula, or M16, which is a very famous nebula. And this is a close-up of one of the parts of that nebula. While there's other stuff here that's shining, the real place where stellar evolution is happening, where stellar formation is happening, is in this dark material, this dark gas that you're seeing in the image. Now, it turns out that there is a minimum amount of, or a minimum size star that you can create, and there is a maximum size star that you can create. You can't create a Jupiter-sized star, and you can't create a star that is 1,000,000 times the size of our sun. And there are reasons for these limitations, and we'll explain them a little later as we go into stellar formation. Stellar formation generally has two main phases. The first phase is starting from raw materials and creating a protostar, which is something we'll explain in a minute. And that protostar will chug along and exist for a long period of time until the core gets hot enough to initiate nuclear fusion in the core. And at that point, that's when we say a star is born, that is a fully fledged star. So let's start with the first phase, which is the stellar formation, the first part of how do we create a protostar. So we start with this cloud of gas, and this is another example of a nebula that has lots of gas in it. Now, what is the size of these clouds of gas in space? They're roughly, on average, 10 to 15 parsecs. Some of them can be larger, some of them can be smaller, but on average, they're between 10 to 15 parsecs. What is a parsec? For those who are not familiar with the term, a parsec is about 3.2 light years across. What is a light year? A light year is about roughly 6 trillion miles. So this is roughly, one parsec is roughly around 20 trillion miles, and we're talking about things that could be 10 to 15 parsecs, so we're looking at something which could be 200 to 300 trillion miles across. These are really, really big clouds of gas, and they are quite cold. They're around 10 to 30 Kelvin, which is slightly above the absolute zero. So this is a couple of 100 degrees below zero. So they're very cold, very dense, comparatively speaking. They've got about 100,000 atoms in every cubic centimeter. And it's a little hard to understand what that density means. So if you think about normal space will have less than one atom in every cubic centimeter. It is a almost perfect vacuum, much better than any vacuum we could create in any lab on Earth. So space is kind of empty, and you'd actually have to look at least 2 cubic centimeters of space to find maybe one atom. So 100,000 in a single cubic centimeter is quite dense. Now, it's nowhere nearly as dense as the air around you. If you think about the air in the room around you, the air in the room around you has about 18 quintillion atoms in every cubic centimeter. So it's not anywhere near as dense as the air that we breathe, but compared to normal space, it is relatively dense. So we have a very, very big cloud of gas, very cold, quite dense, that contains about the mass of maybe 100,000 stars or 100,000 suns. And this gas is pretty much just sitting there. There is some inherent pressure of the molecules of the gas pressing against gravity, but this is a very, very delicate balance. It is so delicate that I would not be exaggerating to say that you could literally sneeze on a cloud of gas like this to disrupt it and start having things start, collapsing. Now, in the absence of humans sneezing on clouds of gas in space, what can trigger a collapse of a cloud like this? And the typical triggers would be two clouds moving close or right next to each other and disrupting each other, and that's causing some turbulence in the cloud. It could be that the cloud is moving through a spiral arm of a galaxy, and gravity is tugging on one part of the cloud, causing it to collapse. Or it could be a distant supernova sending a shockwave through space and disrupting the cloud again. Whatever the trigger is, at that point, the cloud starts clumping. You have gas that is clumping together in clumps that are roughly around a third of a light year across. Now, if you're not familiar with the way Einstein described gravity, I'll take a minute here to describe what's happening here, because it isn't magic. It's a very simple process. If you think about space-time as a fabric, okay, like a sheet that you've got spread out, and you take some mass, an object that has mass, and you drop it into the center of that sheet, it's going to curve the sheet. It's going to create a little well. This is a gravitational well. Anything moving in that well would have to fall down towards the center. And this is what's happening here. As something disrupted this cloud of gas, enough material clumped together to start creating a gravitational pull. And then other material that is around it is going to start falling towards that area where more and more material is accumulating. This is how the process starts. And we're talking about a process that can take 10,000 years. It can take as long as 250,000 years, depending on the amount of mass that we're dealing with. And as the material starts building up, it's starting to condense under gravity. It's starting to build up pressure with friction. Now we're starting to build up heat. And as heat starts building up, when gas gets hot enough, it starts to glow. And initially light is getting out, but as more material starts collapsing on this little ball of gas that we're creating here, it gets more opaque, and now it's trapping in the heat. And ultimately, we get to a point where more material is falling onto this ball of gas, and as it does, the core is contracting and producing more energy, more pressure to balance out that gravity. And now we have an object which is in hydrostatic equilibrium. There's a balance between gravity and pressure. Even as we add more material keeping on falling on and gravity is increasing, so is the pressure. So once we achieve that balance, that is what we call a protostar. And as I said, that process can take anywhere between 10,000 years to 250,000 years. Now, what is also interesting is as this ball of gas is getting hot and it's starting to stream away particles, what we call a solar wind, it's starting to push away some of the material that was initially trying to fall onto it. This material will form as a disk around the protostar. And this disk is what we call the protoplanetary disk. This is the disk of material from which eventually planets will evolve. And you can see it in this depiction, in this image on the right-hand side. The upper part of the image is an artist's depiction of what this process looks like. You can see the protostar here in the middle. It's already a ball of shining gas. And around it, there's still material that is coalescing into a disk around it. In the bottom part of the image, we're seeing the real thing. This is actually a very a close-up image into the Orion Nebula, a nebula that we might be actually seeing later today as we go into the Star Party section of today's event. And this is a very small section, a big close-up into the heart of the Orion Nebula, showing essentially this glowing disk of material, which is essentially the protoplanetary disk, and it's surrounding an empty spot, which is this area that you see over here. The actual protostar itself is so small that you can't see it in this image, but it's in the heart of this empty, dark part of this disk that you're seeing evolving here. And in fact, the Orion Nebula has been studied so often that when astronomers came back to image the nebula and the same disks time after time after time, years over years, at some points you suddenly saw the star ignite. You'd see that point of light appear out of the darkness in the nebula. And that's why we call it a stellar nursery. It's where stars are being born, and we have actually witnessed that with actual images. Once it hits a protostar stage, the star will stay in the stage for as short as 10,000 years and as long as 1 billion years. Again, that really is driven by the mass of the star. A star like our sun was a protostar for about 30 million years. If you take a star that is 30 times the mass of our sun, it will only be there for 10,000 years before it goes to the next stage of its evolution. However, really small stars, let's say a star that is about half the size of our sun, or half the mass of our sun, I should say, uh, will stay a protostar for about 1 billion years. So that lifespan part of a protostar really depends, like everything else, on the mass of the star. So the first phase was creating the protostar. The second point is achieving that thermal equilibrium that I spoke about earlier. So the protostar is still not in thermal equilibrium because it's shining away, and shining away means it's losing heat, it's losing energy into space, and it has no mechanism in the core to compensate for the heat that it's losing. So without that, it's losing heat, and it's following the laws of gases. It's going to contract because gravity is greater than pressure until pressure balances out. It'll build up heat again. It'll lose some of that heat. Pressure will drop. It'll contract because gravity is stronger, and then pressure will go up again, and it will get hotter again. This process can continue throughout the life cycle of the protostar. Again, it could be for 10,000 years, it could be for 1 billion years, up to the point where the core gets so hot that it crosses 10 million degrees Kelvin. And at this point, we're now dealing with a core that is both hot enough and dense enough, because of all the contracting it went through, to enable the conditions that allow protons to start smashing into each other. They're overcoming their electromagnetic repulsion. They start smashing into each other and fusing, and that is the process that starts nuclear fusion in the heart of a star. And now we have an object that is both in hydrostatic equilibrium, the balance between pressure and gravity, and thermal equilibrium. It's generating energy in the core that is equal to the amount of energy that it's losing through luminosity. And that is when a star is born. Now, as I explained earlier, there are limits to how small we can make stars and how big we can make stars. On the lower end, the smallest star that you can make is about 8% the mass of the sun. The reason that we have this limit is because if you went any smaller, then there would simply be not enough mass to continue contracting and driving the heat up to at least 10 million degrees Kelvin. If you had, let's say, only 0.5% the mass of the sun, or 0.4, or if you went to something like Jupiter at 0.2, it simply cannot contract enough to generate enough pressure and heat in the core to reach 10 million Kelvin. That means that nuclear fusion will never ignite. It will never start. And that's what we call a failed star or a brown dwarf, is stars that are around 7%, 6%, objects that are 7% or 6% or smaller than this. So that's the lower limit of why we can't create stars that are smaller than about 8% the mass of the sun. Whereas on the upper limit, we find that we cannot create stars that are bigger than about 100 to 150 times the mass of the sun. And to begin with, those stars are extraordinarily rare. There are not many of them. But the reason we can't make them any bigger, even theoretically, is that if you go to a star that is significantly bigger, the intense amount of radiation created in the core, even in the protostar phase, will be so intense that it will simply shred the star apart and move all the material away, and you will never create a stable enough core to sustain nuclear fusion. So those are the reasons we have these lower and upper limits. You can't go bigger than 100 to 150 times. You can't really go smaller than about 8% the mass of the sun. So that is how stars are born. We start from a very cold cloud of gas. Something triggers it. It starts collapsing on itself, accumulates enough material to create a glowing ball that eventually achieves a hydrostatic equilibrium. Over time, as it contracts, and that time could be, as I said, 10,000 years to 1 billion years, creates enough heat to achieve 10 million degrees Kelvin, and now it starts nuclear fusion, and now we have a stable, balanced star, And that's the way it'll stay for the remainder or the majority of its life, which we'll talk about in the next phase. Let me stop here and see, are there any questions about star formation or how stars are born? Okay. With that, then, let's go to life on the main sequence. And let me explain, first of all, what this diagram means. This is a diagnostic tool. It's called the Hertzsprung-Russell diagram, or HR diagram for short. And it's simply a way that allows us to measure the properties of stars, specifically showing the ratio or the relationship between the luminosity, how bright a star is, and the surface temperature of the star. And as you measure these two elements, you will plot the star. As we measure different stars, we will plot them on this diagram. And what we learn from this diagram is a lot of other attributes of the star, including how long they're going to live and their age. And that's why it's a very relevant tool for us to use in the context of today's discussion. And what you see here in the middle, this main path, starting over here from the upper blue band and all the way down here in the middle, down here to the red area that I'm pointing to with my mouse, this is called the main sequence. This is where stars spend the majority of their lifetime. And in order to be what we consider a main sequence star, this main path, a star needs to meet three conditions. It needs to be in hydrostatic equilibrium, what we already explained, the balance of pressure and gravity. It needs to be in thermal equilibrium, using nuclear fusion to generate energy that is equal to the amount that it's losing through luminosity. And in the core, it needs to be fusing hydrogen into helium, nothing else. If any one of these conditions is not met, the attributes of the star, its luminosity, its surface temperature, will change, and it will move to somewhere else on this diagram. So we'll be referring a lot to this diagram and to this concept of the main sequence, and we'll talk about supergiants and red giants and white dwarfs later. This is where they appear in this diagnostic tool. Now, the lifetime, how long will a star live in this main sequence, is inversely proportional to its mass cubed. Okay, so the bigger it is, the shorter it will live. When you think of a star like our sun, it spent about 30 million years as a protostar. It will spend, and by the way, you can see our sun plotted over here. It's a dwarf star, which is I think it's a G star based on this diagram. Yes, it is. I think it's a G star. And you can see it over here. It spent 30 million years as a protostar. It'll spend 10 billion years on the main sequence. And I just saw a question coming in on the chat. And again, I'm not monitoring it all the time, so I'm hoping Lisa can help me. But I think the question was, are stars being created today? The answer is absolutely yes. And to my point earlier on, we have actually witnessed it firsthand. When we were imaging nebulas of these big clouds of gas, we have actually seen stars igniting, turning on, being born in these nebulae. So star formation is still happening in all galaxies. It's slowing down, but it's still happening across all galaxies. So back to this, we're talking about how long will a star live on the main sequence. Our sun will be on the main sequence for about 10 billion years. So 30 million years as a protostar, 10 billion years on the main sequence. That'll be the majority of its life cycle. Now, if you went to a star that has 10 times the mass of our sun, so now I'm going way up here on the diagram, looking for a 10 mass star, so you can see it's pretty close to what Spica is. Spica is a star that is known to many amateur astronomers. That star is only going to stay on the main sequence for 10 million years. So why do we have this massive gap between one star like our sun shining for 10 billion years on the main sequence and another star like Spica only shining for 10 million years? Because luminosity is proportional to the mass to the power of 4. So the fact that I took a star and made it 10 times bigger, the mass is 10 times bigger, the luminosity is 10,000 times bigger. So this star is shining away 10,000 times more light than our sun. And that means that in the core, in the nuclear fusion, it needs to burn through that fuel 10,000 times faster. So the fact that it has 10 times more mass is actually not that impressive considering it has to burn through it 10,000 times more faster. And that's why big stars have very short life cycles and smaller stars like our sun have longer life cycles. Small stars are like smart cars, the mini European smart cars, where they have very low weight, they have a very small tank of gas, but because they don't weigh that much, it doesn't take much to move them, doesn't require a lot of energy, so they burn through that fuel very slowly and they can go for very long distances. Whereas a big star like Spica is like a big, American Hummer, and it's a big, massive 4-ton car, and just to move it requires a huge amount of energy. And so it may have a massive tank of gas, but it's going to burn through that gas really, really quickly. So the bigger they are, the faster they die. And the other thing that we're going to need to understand before we go further is that there are a few nuances that are important to understand about this process of nuclear fusion inside the stars. So with stars that are up to the size of our sun, or maybe a little bigger, about 1.2, the key process for creating nuclear fusion is the proton-proton chain reaction, directly fusing protons into deuterium and helium-3, and then finally helium-4. As you go into bigger stars, the dominant process for generating energy is known as the CNO cycle. It's essentially still taking hydrogen and converting into helium. If it wasn't doing that, it couldn't be a main sequence star. But the process is different. We're essentially moving protons or smashing protons into different isotopes of carbon and nitrogen and oxygen, and at the end of the day producing helium. But it's a more complex and different process. And these processes are very, very sensitive to even small changes in temperature. Nuclear fusion is very sensitive to the most minute changes in temperature. So in a star that is like our sun, or slightly smaller, slightly bigger, a 10% increase in temperature will drive nuclear fusion up 40%. Just increase temperature by 10%, nuclear fusion goes up 4x, by 40%. If you did the same thing in a bigger star, which is using the CNO cycle, there a 10% increase in temperature will drive a 180% increase in energy production in nuclear fusion. So it is driving nuclear fusion into overdrive. It is a very powerful process. And why does this matter? Because we spoke about the balance of pressure versus gravity. Pressure in the heart of a star is a function of various parameters, temperature, of course, and density. Now, if we're fusing elements, taking, let's say, 4 atoms of hydrogen and creating 1 atom of helium, we are actually causing density to drop. And if we need to maintain pressure and density is dropping, then this object will have to contract and its temperature will have to go up to level things off. So basically, as you'll see when we go through the life cycle of stars, we will get into cycles where the core is contracting and getting hotter, and that heat is going to drive nuclear fusion crazy. And sometimes that produces so much energy that the star can't shine it away. That energy turns into work energy, into kinetic force that is pushing the envelope of the star, increasing the size of the star. And it will make it appear more luminous because it now has more surface area. So it's important to understand that that there's a lot of sensitivity to temperature changes and how they impact nuclear fusion and how that impacts the behavior of the star and what it looks like. Also, it's important to understand that it can also impact the actual physical structure of the star itself. Many of you may have seen diagrams of our sun showing that we have a core that is radiative and we have an envelope that is convective. And that is true about our sun. However, as you go into, and just to make sure that everyone's on the same page here, a radiative core means that the core is really dense. It's not really moving. And the way it releases energy or transfers energy is through radiating heat. If you think about a pot on your stove filled with water, the pot can get really, really hot, but it's not moving. It's still made of metal. But if you touch it, you'll feel the heat. It's radiating heat away. So that's a a radiative way of moving energy. The water inside the pot is bubbling. That is convection. That is how the energy is moving through motion. So when you go to significantly smaller stars, sorry, bigger stars that are greater than 1.2 solar masses, you find that you actually have the core is so hot that it is unstable, and you find that you have a convective core, and the rest of the star, which is really big, but it's really fluffy and puffy, is actually radiative because energy can just move through it quite easily. When you go to stars that are really, really small, let's say 10% or 25% of the size of our sun, you find that both the core and the envelope are both convective. So these things have a lot of implications on the structure of the star. So finishing off on how long can stars live on the main sequence, as I said, a 10 solar mass star like Spica will spend about 10 million years here. A star like our sun will spend about 10 billion years right over here in the lower end of this diagram. Now, when I go all the way down here to a star that is only 10% the mass of our sun, which is what we call a red dwarf, these stars can live for about 10 trillion years. They're very small, they don't have a lot of energy consumption, and they're just happily chugging away, burning a little hydrogen into helium, and they're so small that it's meeting their luminosity needs, and they can stay there for 10 trillion years. Now, if you think about it, our universe is only about 13.7 billion years old. So any red dwarf that was born shortly after the Big Bang is still an infant, still a baby, and it's going to be here for trillions of years more, shining away. So it's kind of interesting to think how long these stars have been around. And then when you go to the upper end, these O and B stars, these big blue stars, they're always, if you're seeing them in the sky, they're always young because they burn through their fuel so quickly and then they die that they cannot last more than a few millions of years. So if you're seeing one of those big blue stars in the sky or big white stars in the sky, they're going to be a few million years old tops because they just don't live longer than that. So that is life on the main sequence. Let me stop here and see, are there any questions about this? I'm just checking, am I coherent or are you just guys too dumbfounded?
I'm good with it. It's good.
I'm fine. I'm fine.
All right.
That's
That's
good.
very good, very clear.
We're all here.
All right.
Awake.
Good deal.
We're awake.
Good deal. Just checking. Okie dokie. So now let's talk about what happens after 10 billion years or after 10 million years when the fuel runs out. And as I said earlier, we're going to converge or we're going to diverge here to two different stories. What happens with low mass stars and what happens with high mass stars. We're going to start with the low mass star. With a low mass star, and we're talking about stars that are typically 4 solar masses or less, this star will spend billions of years fusing hydrogen into helium on the main sequence, happily chugging away. But as it's doing it, the helium that it's creating, if you think about like a fireplace and you're burning wood, a log of wood, there's ash that's being created. The ash is just dropping to the center there, and it's getting really hot, but it's not doing much. And this is what's happening in the core of the star. The helium that was created is just going to condense to the center because it's heavier, and it's building up a core. And that core of helium, while it's very hot, is not really fusing, it's not generating energy, and it is pushing out the hydrogen away. So we have this core of helium in the center, and now we have a shell of hydrogen that is fusing around the helium shell, and the rest of the envelope of the star, whatever makes the rest of the star, is still hydrogen, but it's just really, really hot, but it's not fusing, obviously. And what's happening is, as I said, we're creating less particles in the center because we're going from 4 atoms to 1 every time we fuse hydrogen into helium, and so density is dropping. And now we're losing that balance, that hydrostatic balance that we used to have. And so the core of the star starts contracting on itself. The helium contracts and gets hotter, and it contracts and it gets hotter. And as it's getting hotter, it's impacting the hydrogen fusion happening around it. Remember, a 10% increase to that temperature is going to cause the hydrogen around it to produce 40% more energy, 40% more fusion. Now, the star is generating more energy that it can shine away through luminosity. And that energy is starting to push away the envelope of the star. And the star starts growing and growing. And it gets to a point where which we call a red giant stage. It doesn't happen overnight. This is a process that takes about 1 billion years for the star to grow from the current size of the sun to reaching about roughly 0.7 astronomical units. And again, for those who are not familiar with the term, an astronomical unit is the distance between us and the sun, roughly around 93 million miles. So the sun will grow from that point to 0.7 astronomical units. It'll be right up against us, really brushing up against. It'll fill up our skies, boil away our oceans. It'll engulf the orbits of Mercury and of Venus. They will be basically consumed by the star as it grows. When you look at this from the HR diagram, what is happening here is that the star was originally here on the main sequence. This is a different representation of the HR diagram. This is our sun on the HR diagram, and it is slowly over 1 billion years crawling up this giant phase. And as the star got bigger, it's not necessarily generating more energy. So while it's gotten brighter because it has more surface area to give off light, the surface temperature has actually dropped a bit, and that's why it's trending a little towards the red. That's why we call them red giants. After about 1 billion years, the helium core continues to contract and contract and contract, and as it's contracting, it's getting hotter and hotter until it reaches 100 million degrees Kelvin. And at this point, the helium can start fusing as well. And when helium fuses, it creates carbon. So when you start fusing helium, you start creating carbon. There's some interesting properties about one of the isotopes of carbon called carbon-12, which even though it's not hot enough, it still allows it to fuse a little bit into oxygen. And so we're starting to build up a core that is made of carbon and of oxygen, and that is inert. It's just sitting in the middle, and that is pushing out a shell of helium. As you can see in this diagram, we have the helium fusing around it, and we have the hydrogen fusing around that. Now, because the star found a new source of energy, okay, now it's not only fusing hydrogen, it's also fusing helium. It is now again in both hydrostatic and thermal equilibrium, and so it's starting to trend back towards the main sequence. However, it never really reaches it, and it's what we call a horizontal branch star. So our sun started as a regular star on the main sequence. It grew into a red giant over about, it was here on the main sequence for 10 billion years, then for 1 billion years grew up to be a giant, and then over time, it becomes a horizontal branch star once it taps into the energy of helium that it can tap into. So this process that we just described of helium, the helium fusion phase, it's a very ineffective process. It's only as 1% as effective as hydrogen fuel. And so it'll burn through the helium core within about 100 million years. So if you think about it, we burnt the hydrogen core for 10 billion years. Now we're burning the helium core in 100 million years. And the core of carbon and oxygen, while it's getting very hot, it's about 150 million degrees, it's never going to get hot enough for it to reach the next phase of 600 million degrees, which is required to start fusing carbon. So we now have a core that again is contracting and getting hot, and around it there's a shell of helium, and around that there's the shell of hydrogen that is burning. And because of that, the core is getting more contracted. It's getting hot. It's sending the helium fusion into overdrive. Again, it's really producing a lot more energy, and that energy is again increasing the size of the star. And the size of the star now it won't reach all the way to being a red giant, but it's what we call an asymptotic giant. The word asymptotic literally means trending towards something, but never really getting there. So what we're seeing is a star that started out as a main sequence star, spent 1 billion years climbing up to the red giant star, burning helium for about 100 million years, and dropping over here. And then as the core starts contracting and it's getting hot again and growing again for 10 million years, it will be an asymptotic giant. At the end of that process, what is happening is we have a very unstable environment. The core that keeps on contracting fluctuates the temperature. And these temperature fluctuations are driving the helium fusion process absolutely crazy. And so every few years, it'll just throw out a huge amount of energy. And these are things that we call helium flashes. And they are pushing a huge amount of energy into the envelope that it cannot shine away. And it's literally pushing the envelope away. And it's a process that can take as long as about 100,000 years, pushing that envelope away to a point where the gases that make up the majority of the star that were together with the core from its creation, from its formation, are finally completely separated. And that creates an object that we call a planetary nebula. And this is what we see in this image. This is an image of a very famous nebula that many amateur astronomers have seen, and we might see examples of it tonight in some of the examples people will show us. This is the Ring Nebula, M57, which is part of the summer triangle, which is better to see during the summer. And this nebula is what happens to a star like our sun when it dies. These gases are being heated. The core star that is remaining, the core that remains in the center, is extremely hot, and it's letting off a huge amount of ultraviolet radiation. It's ionizing, it's electrically exciting the gases that used to make up the star. And that's why they're glowing in space, like we're seeing here. It's not artificial. This is what they look like. And over a period of about 10 to 15,000 years, these gases will cool off, and we won't see them anymore. In the next picture, you can see just some other examples of planetary nebulae. I really like them. I think they're among the most beautiful objects in the universe. And the different colors you see and different structures that you see are all driven by different chemical compositions, different temperatures, and rotation aspects of the star involved. So they all have very unique and special characteristics. Some of the more famous ones here, the one I just mentioned, is the Ring Nebula. Over here is the Cat's Eye Nebula, the Butterfly Nebula, the Eskimo Nebula. I believe that today it's given it a different name. But these are just nice little samples of planetary nebula. So this is what happens to a star like our sun after burning for 10 billion years, and then being a red giant for about 1 billion years, and a horizontal branch star for about 100 million years, and then an asymptotic giant for another 10 million years, and it ends up like this: 100,000 years of this gas drifting away, and what is left in the core is a white dwarf. Now, the white dwarf is typically about 0.6 to 0.8 solar masses. It's no longer fusing elements. So how does it stay in balance? You've got all this material. There's still a lot of material there. Think about it. 60 to 80% of what made up the star is still there in the form of a carbon-oxygen core. And there is no fusion. So where is the energy or the force that's balancing out gravity? Well, we now have something else kicking into play here, which is electron degeneracy. Because of certain laws of quantum physics, the Pauli exclusion law, it doesn't allow electrons to inhabit the same energy level. So as the electrons get too close, they repulse each other. And there is a new pressure generated by the electron repulsion that is fighting against gravity and holding this structure together. And it's a kind of an interesting thing, because this pressure is independent of temperature. You could increase temperature, reduce temperature. It will not impact the level of pressure that is generated by this structure. And these objects, as I said, they start out really, really hot. They could be over 100 million degrees in temperature. And it takes them a long, long time to cool off because they're so dense. So an object like this, a white dwarf, can take as long as 10 trillion years to cool off and lose all of its energy. And when it does, it will become a black dwarf. But because, again, that process is so long, black dwarfs in today's universe are a theoretical object. They don't exist yet. They haven't been born yet. We haven't had a white dwarf that has lived long enough to cool off and go black. In the image, you can see here an actual picture of a white dwarf. This is Sirius, the dog star, which is a very bright star. You can see it's the brightest star you can see in the night sky right now, not too far from the to the left of the Orion constellation. And right next to it, something you can't see with the naked eye, is Sirius B, which is a white dwarf. It's a companion of the star Sirius. So if we were to summarize the life cycle of a low mass star, you start out, let's say if it's a star like our sun, maybe 100,000 years to form the protostar, and then about 30 million years as a protostar that is still not in thermal equilibrium. Once nuclear fusion is ignited, this star will be on the main sequence for about 10 billion years. Then about 1 billion years as a red giant, 100 million years as a horizontal branch, 10 million years as an asymptotic giant, then about 100,000 years to become a planetary nebula, and then finally a white dwarf that can take as long as 10 trillion years to cool off.
I have a question about the HR diagram.
Sure.
How wide what is the mass range over which stars form red giants and then go into this horizontal branch? How wide a mass range on the main sequence?
On the main sequence, they can range from, I actually don't know the lower end, to be perfectly honest, because I'm not sure if a red dwarf will ever really reach although technically it should reach a red giant phase, just might be smaller in size. So technically anything from a red dwarf and all the way up to a star that would be smaller than 8 times smaller than 4 times the mass of the sun. The moment you go above 4 times the mass of the sun, it'll actually become a different type of giant, which we'll talk about in a minute. So four solar masses and smaller.
Is it up to F? F class will go into a red giant, and then everything above that will go into the blues.
I believe so. Definitely anything. Yes, below F. G and F will still go to red giants. Above that, it'll go to a different type of giant, a blue giant. Yes. Okay. So just to finish off, there's another way that a white dwarf can end its life, and that is if it is accreting more material onto it. So in some cases, white dwarfs might be a companion to another star, and they might be picking up some material, siphoning off some gas from that star. And if they get to be more than 1.4 or 1.38 solar masses, which is also known as the Chandrasekhar limit, gravity takes over again. At this point, the electron degeneracy simply cannot hold off gravity anymore, and the structure will start crashing on itself. And when it does, it's increasing density, which is causing fusion to ignite. Now we have carbon and oxygen fusing and generating heat, but because this is degenerate matter, it's not increasing pressure. It's not going to increase the size of the structure. So we're basically, pressure isn't going up, the collapse is continuing to happen, and as density increases, it's driving more heat and more nuclear fusion until the whole star detonates in a supernova. And that is known as a supernova type 1a. And the nice thing about supernovas type 1a is the fact that because we know that they can only happen with an object that is about 1.4 solar masses, and we know the chemical composition of it, we know exactly how much energy within a certain range it's supposed to produce. Therefore, its luminosity is intrinsic. We know exactly how much energy, how much light it's supposed to produce. And therefore, when we see different supernovas type 1a, and we see the one is brighter than the other, the difference in luminance is purely because of distance. And that's why supernova type 1a are very useful standard candles that are used in astronomy and cosmology research. So they're very useful little tools, and actually were instrumental in the research that was done about 20 years ago, proving that the universe is not only expanding but accelerating its expansion. It was done through the research of hundreds of supernova type 1a explosions. So that's another way that if it doesn't cool off and become a black dwarf, it can actually reach a supernova type 1a and explode if it was accreting more material. Now let's go to the other branch of our story, which is to high mass stars. And you'll see that our story here differentiates again because there's a story that happens to stars that are between 4 to 8 solar masses, and the story changes again once you go above 8 solar masses, and we'll explain those differences in a minute. So when we go to a star that is more than 4 solar masses, we can go beyond a core that is made of carbon and oxygen. Remember that in the stars that were smaller, we had a hydrogen and helium, and we were fusing into carbon and oxygen, and then it just sat there. It could not get hot enough for it to continue the fusion process in the core. But when there is enough mass above 4 solar masses, we're now going to go through a different cycle. And as I said, we're going to look at stars that are from 4 to 8 solar masses first. Those stars will climb up the red giant branch within 1 million years. So below 4 solar masses, it could take them 1 billion years to go from the main sequence to being a red giant. With these stars, the process is so fast, it can be done in about 1 million years. And the size of this giant, this red giant, could be as much as 5 astronomical units. So just to be clear, we're talking about an object, a star, where the center is where our sun is, and the outer layer is where Jupiter is. So everything, including Mercury and Venus and Earth and Mars and the asteroid belt, all the way up into Jupiter, would be inside the star. That's how massive the star can get. And when the core, reaches 100 million Kelvin, like we said before, helium fusion starts, and the star, regains hydrostatic equilibrium and thermal balance. It becomes hotter, and it becomes a blue supergiant, which is a different location on the HR diagram. So instead of going, our stars over here, stars that are smaller will climb up this giant branch, but bigger stars will climb over into the blue supergiant branch, and they'll cross over this distance in about 1 million years, whereas climbing up here took about 1 billion. And it's all rated to the rate of the nuclear fusion derived from the mass of the star and its needs for luminosity. So the amount of nuclear fusion required for a blue supergiant is huge, and it can last for about 1 million years. So if you're seeing a blue supergiant in the sky, it cannot be older than about 1 million years. It simply cannot last longer. As we're building a core of carbon and oxygen in the center, and the helium and the hydrogen get pushed out into the shells around it, the star is losing that hydrostatic balance, and it's starting to contract a bit. And so it moves over to be a super red giant. So it never goes to be a red giant, because it's still a massive star. It becomes a super red giant. And one of the more famous ones is Betelgeuse, which you can see here on the diagram. And that is part of the Orion constellation, the left corner shoulder of Orion. And it's not something I'm sure we'll see today, but you can see it naked eye if you go outside. When the core density of the carbon oxygen core reaches 155 grams per cube centimeter, which is 155,000 times more dense than water, and 600 million Kelvin. Now we reach the conditions that carbon fusion can begin, and now we're producing a situation where the star will never regain its balance. So at this point, the rate of fusion is so fast and so inefficient that it can no longer compensate for the energy loss for its luminosity. And the byproducts of fusing carbon and a little bit of the oxygen there is producing more oxygen, neon, and magnesium. So now in this star, we're building a core that is made of oxygen, neon, and magnesium. Around it, we have a shell of carbon that is fusing. Around that, a shell of helium that is fusing. And around that, still a shell of hydrogen that is fusing. This process is fast. It's taking about 1,000 years. That's how quickly it goes. So we've gone from billions down to 1,000,000, now down to about 1,000 years of burning in this way. And as we continue to contract this core of oxygen, neon, and magnesium, it also is contracting and increasing its temperature. That temperature is driving the nuclear fusion around it way crazy, sending out flashes. They're going to push away that envelope. And really kind of depends on how big the star is. It could produce a very large planetary nebula, but in some cases, the process is so fast and so violent, it doesn't leave anything. It just pushes all those gases away, and they don't remain close enough to the star to create that beautiful object. And what is remaining behind is a white dwarf, like you saw before, but it's made of slightly different materials, oxygen, neon, and magnesium. And it'll be slightly bigger. It'll be about 1 solar mass. So now we're going to go further up to stars that are bigger than 8 solar masses and see what happens to them. In those solar masses, the process doesn't stop. It continues. And when the core continues to contract and get hotter and contract and get hotter and contract and get hotter, you get to a point where the oxygen, neon, and magnesium core reaches 1.5 billion degrees Kelvin and over 1 million grams per cubed centimeter. Now neon can start fusing. Now this process is extremely inefficient, and the star is shining brighter in neutrinos than it is in photons. It's letting off huge amounts of neutrinos, which are these very small particles. We gave this example, by the way, last time, and I'll repeat it here because it'll be relevant as we go down the story. A neutrino is a very small particle, almost no mass, has a little bit of mass, but almost no mass, no electrical charge, and it's moving almost at the speed of light. It is so small that you could take 20 trillion miles of lead and shoot 10 neutrinos through it, and 7 of them will come out the other side as if it wasn't even there. Through every square inch of our body, we have about 60 billion neutrinos going through us every second, emanating from the heart of the sun. So these are really small particles with a huge amount of energy that are just flowing out. Right now, there's a bigger amount of those than there are photons generating light for this star. And this process of burning neon in the core will be fast. It'll only last for a decade. So the process is continuing to accelerate. Now the core is compressed. We have neon, and we have burning shells of carbon and helium and hydrogen. When the core reaches 2.1 billion degrees, that ignites oxygen nuclear fusion. Now oxygen nuclei are starting to fuse, and the energy loss is prodigious. Now for every single photon that we're producing 100,000 neutrinos, which are flowing out. And within a single year, that process will produce a core made of silicon. So we've gone from billions of years of fusing hydrogen to hundreds of millions of years, or 100 million years of fusing helium, to maybe 1,000,000 years of carbon. Now we're fusing neon in a decade. We're fusing oxygen into silicon within a year. We create a core that is made of silicon. So we now have this object with 3.5 billion degrees Kelvin, density in the tens of millions of grams per cubed centimeter. And this fusion that is happening in all these onion layers, you can see all the layers of fusion here. We have hydrogen fusion and helium fusion and carbon and oxygen and neon and magnesium fusion. And in the core, we're starting to create silicon fusion. There are other sub-elements that are created in the process that you could start filling out the periodic table. Potassium and sulfur and phosphorus and calcium, they're all created in this process until we reach a point where we've created an iron nickel core. And this big core that took a year to create of oxygen fusing into silicon, this one big core will now fuse in one single day to iron and nickel. So we're talking about an object which is about the size, the mass of the sun, fusing in a single day into iron and nickel. And then the process stops. And the process stops because the process of trying to fuse iron is an endothermic process, and nature doesn't like that. Nature doesn't like to invest more energy than it's going to get. Also, the mass ratio doesn't work anymore. The amount of mass you would have to invest to fuse, and the byproducts of that fusion process actually weigh less than what you've invested. So the process basically stops. There is no more nuclear fusion happening in the core. We have a project that we have an object that is getting more and more dense. It continues to contract in itself, even though it's not fusing. The temperatures reach around 4 billion degrees Kelvin. And there is no fusion that's going to ignite from this contraction process. There is nothing left to fight gravity. And there is only one way to continue from here, and that is going to be death via supernova. So follow me now into the heart of a supernova. Now, to recap our story up until this point, we had a star, we're talking about a big star now, so it only spent maybe 10,000 years as a protostar. It spent about 10 million years on the main sequence, fusing hydrogen into helium, then 1 million years as a supergiant, and then another 1,000 years burning neon in the core, a decade burning the oxygen, and then a year building up the silicon, and now we're left with 1 day converting it all into iron and nickel. And all these processes now are not producing enough energy to fight off gravity, and there is no fusion happening in the core, this big core that is sitting there getting really hot, but it's not going to produce fusion. And now the next steps are going to take literally seconds and milliseconds. So the core is not fusing, it's not fighting, there's nothing left to fight gravity. And as you can see, it's starting to condense. This blue area here is representing that core, that big iron core, iron nickel core in the center. And it's starting to collapse against itself. As it's collapsing, it's getting hotter and hotter. It's going to reach 10 billion degrees and a density of 10 billion grams per cubic centimeter. At this point, nuclei start to melt together. It is disintegrating. It's starting to fall, disintegrate into lighter elements. And this process, in the final few seconds, we're seeing protons and electrons merging and creating neutrons, releasing an ocean of neutrinos. And that is literally pulling the bottom out of this core. And it's now going to go into an absolutely catastrophic process. The energy's been dropping, pressure is dropping, gravity is taking over. When in the next two phases, and again, pay attention to this blue circle in the center, we're starting off with an object which is around almost the size of the Earth, about 6,000 miles, a ball of iron and nickel, about 6,000 miles in size. 1 second later, it is about the size of a city. An object made of iron, about the size of the Earth, is condensed to something the size of, a large metropolitan city with a ridiculous density. Now, this process is so fast that the collapse of the core, this collapse of the core dropping down is happening almost at 25% the speed of light. But when it gets to that very dense level, it gets so dense it has the same density as a nuclei. Essentially, we're looking at a proton the size of a city. It is a big, big, big nuclei. And now a new force of nature takes over, which is known as the strong nuclear force. And that is a repulsing force. It repulses back, and it causes the core to bounce back at incredible speeds, at a speed of about 50% the speed of light. So now this core bounces out at 50%. But guess what? That's happening in the center. And we're talking about a star that the edge of it is somewhere near Jupiter and all the stuff in the middle, right? So all the rest of the star doesn't know that the core has decided to bounce back up because the strong nuclear force woke up. And so the rest of the star is collapsing down still at 25% the speed of light. So we now have the core bouncing back at 50% of the speed of the light and the rest of the star bouncing down at 25% of the speed of light, it's going to create a pretty fantastic experience. So what's happening now is it's creating this traffic jam of all these particles, and the neutrinos that are generated in that core bounce that are coming out of the core are now not able to get out. They are actually bouncing into this strong nuclear material that is millions of times more dense than lead. They're not getting out. They're driving temperature and pressure up to the point where it can push away everything, the whole envelope explosively away in a matter of milliseconds. That is the moment of the supernova itself. And there is enough energy being released now to drive explosive nuclear synthesis throughout the envelope. Until now, remember, fusion was only happening in the core. Now there's so much heat and the temperatures are being driven to such ridiculous levels. There's so much free energy being flown out there that nuclear fusion is happening everywhere in the star. In fact, there's so much free energy there that you can start slamming neutrons into the nuclei of iron, starting to create elements like gold and platinum, which are created in the very last moments of a supernova. Now, because all this is happening in the core of the star, and the core is, in the center, and the edge of the star, the envelope of the star, the outer envelope, is 500 million miles away. It actually takes time for that process to travel throughout the structure of the star. So even though the core collapse in the supernova happened in a matter of milliseconds, it can take actually hours for that to propagate throughout the entire star until it reaches the outer layers of the star and breaches out, and the whole star explodes. And that's when we see the supernova, and it is an object that shines as strongly as 10 billion stars. That is the process of a supernova. And what is left behind kind of depends on the size and the mass of what we started with. If the core was around 2 solar masses, again, which would mean that the originating star was between 8 solar masses to around 18 solar masses, you would have a core of iron that's around 1.5 to 2 solar masses. That star will leave behind, that explosion will leave behind a neutron star, which is all those electrons and protons that merged into neutrons and stay together. It's an incredibly dense object. We're talking about an object that could be 1.5 solar masses, about tied into the size of the island of Manhattan. It is ridiculously dense and has a lot of strange properties to it. If the core is bigger, if it's more than 2 solar masses and potentially larger than 3 solar masses, then that collapse will continue and it'll create a black hole. And to do that, you need a starting star, which is at least 18 times 18 times the size of the sun or more. And we'll talk more about black holes in a minute. But to quickly recap the life cycle of high mass stars, we have a very fast formation period. Instead of 100,000 years, it might be only 10,000. It will be a protostar for about 10,000 years, not 30 million like a small star. It'll stay on the main sequence for 10 million years versus 10 billion. It'll be a blue giant for about 1 million years versus a red giant, which could be about 1 billion years. Then a red supergiant for another 1 million years. It'll be burning an oxygen core for about 1,000 years. The silicon core will build up over a decade, and then within 1 day, it will convert into an iron core. And that is the life cycle of large stars. Now, a couple of words about black holes. As I said, if the core is more than 2 or 3 solar masses, neutron degeneracy can no longer hold against gravity. So even the neutrons are not dense enough and creating enough pressure to fight off gravity at this point. And this is the ultimate win of gravity. It's going to collapse even further and collapse on itself. It creates an object that it has almost infinite density and has almost no size, which is a very strange thing, and it's what we call a singularity. And this singularity has so much gravity that it is warping and wrapping space-time around itself. And the gravity pull is so strong that nothing can escape from it, not even light, which is why we call it a black hole. I think there was a comment that just came in about it looks like the Earth is made of the leftovers of these processes. That is absolutely correct. So, the Earth is primarily made of an iron core, which comes from, the iron made in the core of stars, and the silicon that we have here, and the calcium and the carbon and everything that we are was made in stars and then got exploded into the interstellar medium through a supernova, and then we're recycling it and using it to create planets and people and computers. So
Right, we're the product of a second generation star, right? Our sun is a second generation star. So
I think it's even more than that. I think that I read somewhere that we're a fifth generation star.
fifth generation star. Okay, well, it's one that's been around for a lot, that was created out of material based off of the more stars that had some of these elements. So that's why, like gold that we have, to your thing, is all come from a supernova. All the gold on our planet is basically from a supernova, but that was reminiscence of previous stars that had blown, and then that gas that is expelled out eventually gets reconglomerated into other clouds that form new stars, and that's sort of what the generational stars things.
Correct. So
there's one. Sorry, one other question was how are the heaviest elements being created? Maybe they're speaking of uranium and things like that.
So most of these are also created in the final stages of a supernova. Most of these heavier elements are created in that, because there is no other mechanism for us to create them. There are a few artificially created elements on the periodic table, but most of them are created in the final stages of a supernova.
And certainly any stable element, right? Because there's tons of elements on the chart that are unstable, but all the stable ones are made off.
Correct. So a few more words about black holes. Black holes, they don't really have a surface.
I think there is another mechanism.
What is that?
Neutron star collision.
Correct. So black holes are really hard to describe, because in many depictions, like the one I just picked here from the internet, it kind of looks like a black ball, but it really isn't a ball. It doesn't have a surface, because it has a singularity, and then it's causing a huge distortion to space-time. We call them black holes because once something goes into them, it can't come back, and they're black, and we don't see anything in them, so we call them black holes. There is a radius, which is called the Schwarzschild radius, which was calculated by a young German physicist during World War I, which tells you what is the minimal distance you need to be away from the singularity. And this radius represents the point beyond which no information and not even light can be returned. So we don't know what's going on any closer than that radius. That is also sometimes referred to as the event horizon, which is the name of our newsletter. It's the point beyond which we cannot get any more information. And because we're using a radius to depict that, we tend to depict them as a ball, because they have a radius that they're affecting, but they aren't really a ball. They don't really have a surface in the traditional sense that we know it. Now, we can't see black holes directly, but we can measure their impact on their surroundings. So if you have, and about 50% of the stars in the galaxy do live in binary systems where it's two stars right next to each other. One of them may have gone through a supernova, a core collapse supernova called supernova type 2, and collapsed into a black hole. And now you're going to see one star rotating around nothing. Okay, and that nothing, you can measure the impact, the radial velocity and the Doppler effects, and you can actually measure what object is there and what gravity it has. So we can see the impact that they have, but we can't see them directly. We can also sometimes, if you're lucky enough, that star might be so close that the black hole is siphoning material away from the star, and that material is accreting in a disk around that black hole as it's falling into the black hole, or falling onto the black hole, I should say, and then you can see an accretion disk forming. So those are the ways that we can see black holes, but there is no direct way to see it. And just to twist your head around all this a little more, there's this thing called Hawking's radiation, which is basically a form of radiation where once every few billions of years, an atom might escape, or a little big piece of radiation escapes from a black hole. And if you wait long enough, specifically it's calculated to be around 10 to the power of 73, that's 1 with 73 zeros after it. If you wait that long in terms of years, this black hole will evaporate into nothing, which is another mind bender. So that is how large stars can end their lives. They can end their lives as neutron stars. They can end their lives as black holes. Now, the key, comment after all of this is, how do we really know? How do we test this theory of stellar evolution? And how can we tell? I mean, astrophysics, modern astrophysics, has been around for less than 100 years, or about 100. No, it's a little more than 100 years now, I should say. But we're talking about objects that are living millions of years and billions of years. So how can we make any observation in any level, with any high degree of certainty? And you would be faced with the same problem if you were to try to study the life cycle of a tree. If you wanted to study the life cycle of a tree, some oak trees can live as long as 400 to 600 years. So how can we make any claims? How can a single researcher make any claims about the life cycle of a tree? And studying a single tree would be, very difficult to conclude any real information from. So from one tree, you can't learn a lot. But if you went to a forest in a single afternoon, you could see, saplings and acorns and middle-aged trees and dead trees. You could see every stage of that evolutionary phase of the tree. And from that, you can deduce something about the life cycle of the tree. And the same thing applies to stars. So when we study the life cycle of stars, we're not necessarily looking at a single star, but we're looking at clusters. Now, this is actually an image I took of the Pleiades a couple of months ago. So when we look at a bunch of stars, we can learn something about them. And the reason star clusters are so helpful, and I'll soon explain a little more about these two different types of star clusters, is because these clusters were generally formed from the same nebula, which means that they were made from pretty much similar materials. They have very similar chemical compositions. They're moving generally in the same direction in space. They are roughly around the same distance from us. So there's a lot of commonality in these stars, that when you are starting to detect differences in their luminosity, it's because of intrinsic values of the actual, or characteristics of the actual star. It's not because of different distances or different chemical compositions or different angles of motion. So that's why studying a cluster really helps you learn more. It's a more reliable way to understand more about the age of stars and their evolution. And what you can see in this picture here, the upper picture is a globular cluster called M5. It's a very, globular clusters are very dense clusters which rotate like they're bound by gravity. The stars are so close that they can't move away from each other, and they're moving as a ball around the halo of our galaxy. They tend to include very, very old stars, typically 10 billion years or older. The cluster at the bottom is a young cluster. This is the Pleiades, which M45, which the stars there are roughly around 100 million years old, so they're technically babies, comparatively speaking. Now, what I'm going to show you next is the HR diagram, the Hertzsprung-Russell diagram of each one of these clusters. So at the top, you're going to see the M5 diagram. At the bottom, you're going to see M45 or the Pleiades. And what you can see here is these diagrams are completely different. And they're telling you a story about the age of these stars. You see, when I look at the upper diagram, what I see is a bunch of red dwarfs. And yeah, red dwarfs, we know they're going to last forever. They're going to, 10 trillion years. So I'm not surprised to see a lot of those. I can see some horizontal branch stars, late stars, and I can also see some red giants. What I'm not seeing on this diagram are any blue O and B stars, because the stars here are just too old. If there were any O and B stars in this cluster, they died, billions of years ago. So I don't see it. This is an old cluster. It's showing me the age of these stars. Where I look at the bottom diagram, the Pleiades, these are all young babies. Look at them. How many blue, big O and B stars, filling this diagram. So the HR diagram is one solid way that when we analyze clusters of stars, we can understand quite a bit about their age and about their evolutionary cycle. And then when I look at the different stars inside the cluster, if there's a difference between them, it is because they're in different stages of their own evolution. In addition to that, of course, we have lots of evidence, observational evidence of protostars, of planetary nebula, of supernovas, of black holes. So there is a lot of evidence, a big, massive body of evidence to suggest that our understanding of stellar evolution is quite on solid ground. And so to summarize where we started from, stars form from clouds of gas in space. And if they're really, really big stars, they will live a very short life cycle. They'll turn into a massive star. They'll become a super red giant, super blue giant, and then a red supergiant, and then they will end their lives as a supernova. And depending on how big the star is, if the star was 18 solar masses or smaller, it'll end up as a neutron star. If it's bigger than 18 solar masses, it will end up as a black hole. If the star was between 10% and as high as 8 solar masses, 10% of a solar mass all the way up to 8 solar masses, it will become a red giant, turn into a planetary nebula, and end life as a white dwarf. And the core, depending on the size, if it's up to 4 solar masses, it'll be carbon and oxygen. If it's greater than that, it'll be neon, oxygen, magnesium. But at the end of the day, it's a white dwarf with very similar attributes. That is the life cycle of stars. And as Michael mentioned earlier, if you have any piece of jewelry made of iron or gold, it was forged in the dying seconds of a massive star exploding in a supernova. And whenever you feel a little small and insecure, remember that the calcium that makes up the bones in your body, and the carbon that you're made of, and the iron that turns our blood red, all of those elements were created in the core of stars. And in that sense, we are all very much, in a very real sense, stardust, which kind of makes us all special. So that concludes my talk for this evening. And I'd like to open it up for any other further questions, or to hand it back to Mike.
I had
wow, what do they do for an encore?
Well, we need an actual supernova then. Actually, we did have one actually in the NGC 514 a few months ago.
Right.
There's actually one this month in 4414.
Oh, interesting. Okay.
Yep. Been trying to get a picture of it. I have a bad one. I had a quick little, I guess, sort of comment a bit on the stuff you were talking about, the cold gas. There's astrophysicist that I've been following who's studying the quenching of galaxies, which means when galaxies stop producing stars, and trying to figure out what causes that, what causes that happens. And one of the interesting things, sort of related to what you're talking about, is if the gas in the galaxy becomes hot or heated, then it can never, the energy from that heat keeps it from condensing, and it stops making stars. It's one of the ways that condense. So one of the things she's trying to uncover is, like, when galaxies collide, it can or get near each other or things like that, it can heat up the gas that is in the galaxy, and actually prevent stars from ever being formed in that galaxy again, and thus quench it to where that galaxy will eventually die as all the stars go away. Yeah, the thing is, as galaxies collide, they reshape. And typically, if you think of the one that is most pertinent to us, which is the Andromeda galaxy and the Milky Way galaxy, when most models today show that when those two galaxies collide, they will become an elliptical galaxy. They'll no longer be a spiral galaxy. And typically in elliptical galaxies, which is a lot of galaxies that you see out there, they have very little, if none at all, star formation after the merging of galaxies. Yeah, she's been studying a lot of this stuff recently, and some new topics of different things that cause quenching. She studies a lot of bar galaxies and how that affects star formation. And to your point, many elliptical galaxies are quenched or coming into the quench. But there's a whole bunch of new research too that she's uncovering that sort of things that sometimes collisions don't necessarily cause quenching, and so there's still a lot of mystery in these areas. So she's been interesting to follow on this topic, since that's her field of research.
I have a couple of questions.
Chanan?
One at a time.
Yeah,
I think that Philip had a question. All right, Ed, why don't you go first?
Okay. So you said on a sun-like mass is it will spend about 10 billion years on the
Main sequence.
on the main sequence.
Yeah.
Is the 10 billion years sort of the same measurement of time as for how long the universe has existed? And and if it is, then for the red dwarfs who take longer than 10 billion years or 15 billion years or 100 billion years to reach whatever they're going to, is we actually don't know what they will turn into in the end. Do we, or are
We
there
don't.
ways to be able to?
So there are the only way we know is based on theoretical models, because as I said earlier, when our sun was created around 5 billion years ago, so the universe at that point was roughly already around 8 billion years old, no problem. However, a red dwarf that was created, let's say 500 million years after the Big Bang, is still around, and it's only 13 billion years old, or 13.2 billion years old, and at least the theoretical models show that it could continue, and every indication shows it'll continue to be on the main sequence for another 10 trillion years. So how long it lives and how how it evolves into a red giant and so on and so forth is completely based on theoretical models. There's no observational evidence to see it because it hasn't happened yet.
Yes, okay.
Philip, I think you had a question?
Yeah, I think, well, thank you for a really excellent detailed talk. I've never seen anywhere near this much detail on the subject before. Just two things that sounded contradictory. You said that hydrogen fusion lasts for or goes for stars that are up to 1.2 solar masses, and then later in the talk, I thought I heard you say it continues for stars that are up to 4 solar masses. Can you clarify?
Sure.
That?
So, first of all, when we talk about hydrogen in the core of a star, the core of the star is highly ionized. So you have a sea of protons and you have a sea of electrons. The hydrogen is not in molecular form; it is in ionized form, where it's essentially a single proton floating around. And so when we talk about fusion, we're really fusing protons. Let's first of all clarify that. And what I was explaining was that at stars up to 1.2 solar masses, the dominant process for nuclear fusion is called the proton-proton chain reaction. It's a process where you smash 2 protons together and you produce deuterium, which is a proton and a neutron. Then you're smashing another proton into the deuterium and you're producing helium-3. And then you smash 2 helium-3 atoms together and it produces helium-4 and releases 2 protons into the mix. And in the process, it's releasing all sorts of gamma rays and neutrinos and positrons and photons and all sorts of fun stuff. In stars that are bigger than 1.2 solar masses, that's when we're dealing with a slightly different process. We're still fusing hydrogen into helium, but the process is no longer the proton-proton chain reaction. The process is now called the CNO cycle. And CNO, it means carbon, nitrogen, and oxygen, where there are trace elements of all of these in the core of the star. They're there. And the proton is fusing with different isotopes, creating different compounds that eventually at the end release helium. So I'm starting with a process that goes from hydrogen and end with helium, but instead of going, smashing a proton to proton and going very direct, I'm going through a process called the CNO cycle, where I'm using isotopes of carbon, nitrogen, and oxygen to manage the process, and it is simply a process that is a lot more sensitive to temperature changes, and that's why I called it out, because temperature changes is what is fueling changes in nuclear fusion and in the structure of the star over time.
Got it. Thank you. The other question, I've heard in other talks that when stars get bigger still, they don't generate supernovae, but they just basically disintegrate. Can you comment on that?
There's rare stars like Wolf-Rayet stars and a few others that get, especially on the very high end of the spectrum, like 150 times the solar mass, where they shred themselves apart and leave nothing behind. And so that happens on the very high end, and they're very, very rare stars. Very few of them in every galaxy.
Thank you.
Sure.
We have a question from the chat. What does this cycle of stars mean in terms of whether there's life, perhaps not in our galaxy, but with other stars similar to our sun?
Well, generally speaking, the likelihood of life evolving around a O or B star are just not very good, because the life cycle is so short, the radiation is so intense, and the end is so violent that it's just not likely that around big blue stars you're going to find planets that had evolution and life evolving around them. That said, the majority of planets in the universe are actually 85% of the stars in our galaxy, and from what we understand in other galaxies, are going to be the dwarfs, the ones that start from our sun and actually go smaller down into the red dwarf phase. And those stars have very stable and long cycles, which are conducive to allow life to evolve around them. So basically, based on the sheer size of the number, I should say, the sheer number of stable stars out there, it would indicate that, at least statistically, life is possible. Now, the life is very probable, I should say. Now, again, we have to sort of distinguish between life, which is microbial life, versus intelligent and technologically enabled life. That's a pretty big gap between the two, billions of years gap, to be precise. I think the revised version of the Drake equation, which is something you can look up, would indicate that in any given moment, every galaxy has one intelligent, technologically enabled society in the galaxy, which, by the way, would spell out that there are 2 trillion of them in the universe at this point, but we're kind of far apart in terms of our ability to engage. Any other questions?
That's true both from the standpoint of time as well as the standpoint of distance.
Yep.
I have one more question on the numerical distribution of stars over time. Were there more bigger stars in the beginning of the universe, and they've been fragmented into smaller and smaller and smaller, longer and longer and longer lived stars? Or is there any, what can you comment on that question?
It's a great question, Ed, and I'm not sure I know the correct answer. So I'm completely postulating here. This is not based on knowledge. But I would assume that it is likely there were more in the past, just because they don't live long and they explode and die. But I wouldn't, so it is potentially there was a higher percentage number of them and an absolute number of them, but I still wouldn't assume that at any point they were the majority or even the norm, because you still need a huge amount of material to coalesce to create the star in the first place. And it's quote unquote easier to create smaller stars. And nature tends to like things that are easier. So I would assume, and again, this is just me postulating here, that there was a higher number, but it wasn't like drastically 50-50, or at any point that they were the majority. I think that it was always geared towards the smaller stars.
I think I read somewhere there's been more that in the beginning there were more red dwarfs. There were more smaller stars and larger stars, and it's one of the reasons why we have so many left now, because, like, to your point, the red dwarfs last longer than the than the universe has been formed.
I read just the opposite, that at the beginning, when star formation became visible, that there were the first stars, the ones that had low metallicity, were actually blue stars.
No. I mean, as I said, I'm not speaking from knowledge here, so it was me guessing. It would be interesting to understand that theory, especially when at least in one place we have evidence to suggest otherwise, which is the globular clusters. Globular clusters like M13 or M22, which range in age from 10 to 12 billion years, which is not as old as the universe, but pretty old. Those stars are population 2 stars. They have very low metallicity, so there's not a lot of metal in those stars.
But hasn't the mass distribution of across space sort of become more stringy like?
It
In a
has.
sense? And does that indicate anything? I have no idea.
I don't know, but I think that if you're talking about stringy in the sense of these strands of material and vast voids of nothing, then I think the most recent theories I've seen about that 10 years ago was around the distribution of dark matter. And the dark matter was with the structure of dark matter in space is the construct, around which the visible matter started coalescing. So I think it's more tied to that than it is anything else.
Yeah, that's what I've read too. The stringiness is all based off of the gravity of dark matter, more than the gravity of stars and galaxies.
Yeah. Well, anyway, I hope you guys enjoyed it. I enjoyed speaking about it.